Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're looking at one of the most important theorems in linear algebra, the Rank Nullity Theorem. In the last video in the Oxford Linear Algebra series, we introduced the concept of a linear transformation, a map between vector spaces which preserves their structure. We'll see linear maps again here, as well as another concept we've covered before, the dimension of a vector space. Before I state the theorem, we first need to define two important concepts, the kernel of a linear transformation and the image of a linear transformation. Suppose we have a linear map T, which is going from V to W. So T from V to W, a linear transformation. Then the kernel of the map T consists of the set of all vectors in our space V which are mapped to 0. So it's everything in V that is mapped to 0 under the map T. So formally, we would say the kernel of the map T is defined to be the set of vectors in V such that T applied to any of those vectors gives you 0. And similarly, the image of the map T, image of T, is going to be everything that T maps to. So this is going to be defined as the set of TV such that V belongs to our vector space, capital V. Now it's fairly straightforward to show that both of these are subspaces. So the kernel of T is going to be a subspace of the starting space V, and the image of T, everything that's mapped into by T, this therefore is going to be a subspace of the finishing space W. And you would just simply check this using the subspace test, which was covered in an earlier video in the Oxford Linear Algebra series. And I do recommend actually doing this. It's a very helpful way to check your understanding of not only the subspace test, but also to make sure you understand the concept of the kernel and the image. For a concrete example, let's consider the following map. So suppose we have a map T, which is going to go from R2, so that's going to be the Cartesian plane, XY plane, and it's going to also map into R2, and if we input a general point xy as our 2 vector, then this outputs x. Now we want to calculate the kernel and the image of this particular map, but I think in this instance the best way to do this is actually to first understand what the map is doing, and we're going to do that by drawing a picture. So we're working in R2, so let's draw ourselves some axes, so this is x and y. And let's suppose we're at some point, let's suppose it's down here, and call this the point xy. So this is our input into this map T. Now this outputs the coordinate position xx. So we can see that x doesn't change, but we move up to a new position x on the y-axis. So it kind of shifts that point up vertically. And now if I had a different position, maybe I was over here, so let's say that's x1, and this one was now x2, and we have a different y value as well, of course. But again, under this map, so that's x1, y1, this is x2, y2. So this is now going to go to the y value up here of x2. So this one up here is going to be x2, x2. And this one is, of course, x1, x1. So what we can see this map is doing is it leaves the x coordinate unchanged, but it basically moves the y coordinate to also be equal to the x coordinate. And if, in fact, if I were to draw a straight line here, assuming my diagram is reasonably accurate, that's not too bad, better than I thought it would be, this is actually going to be the line y equals x. So what the map is doing is taking our input, some point xy, it's leaving the x value unchanged and it's moving the y value so that we lie on the line y equals x. So we can immediately see that everything that comes out lies on the line y equals x. So the image of this map is just the line y equals x. Simple as that. And the kernel we can think about as which points, so it equals points xy such that t of xy, which is given by xx, so such that xx is equal to 0, 0. Because this is t of xy. And 0, 0 is, of course, the 0 vector in our output space. So if xx equals 0, 0, well, that's only true. This is only true if and only if x itself is 0. And we don't actually care about the value of y. So if we had any point here, or here, or here, or even for a negative value of y, all of those points, x is 0 along the y-axis, and all of those points, therefore it would be 0, y would just go to 0, 0. They would all go to 0. So anything along the y-axis, so y can be any value, but x has to be 0. So therefore, the kernel of this map is going to be equal to the y-axis. Now it's at this point in the video that I'm going to bring in the second topic I mentioned at the beginning, which is that of the dimension of a vector space. So we're going to make a further pair of definitions. So we have the kernel of a linear map, which I've told you is a subspace, and you've hopefully checked that by now. What we're going to consider is the dimension of the kernel. So the dimension of the kernel of T, and we're going to define this to be the nullity of the map T. So the kernel is a valid subspace. It therefore has a basis. We can count the number of basis vectors, and we know that that's going to give us the dimension. And we call that the nullity. Now we do the same with the image. So we're going to say the dimension of the image of T, which again is a subspace, so it will have a basis, and we can count those basis vectors. And that dimension is what we're going to call the rank of the map T. So this is the rank of T. And as you may have guessed, rank and nullity are exactly the two terms mentioned in the big theorem, the rank nullity theorem. So in our example, we can say the dimension of the kernel, or the nullity of our map, is equal to the dimension of the y-axis. And if we think about a general point on the y-axis, it is just some number y multiplied by the vector 0, 1. So any point on the y-axis is given by a real number y multiplied by one of our basis vectors, 0, 1. So therefore this is one-dimensional. And so we can say, in this instance, the nullity of the map is equal to 1. We can now also look at the image, which is our line y equals x. And if we think about how we would construct any point on that line, well, that's simply some number x multiplied by the vector 1, 1. So any point on this line, and therefore any point in our image space, is a real number x multiplying a single vector 1, 1. So this again is going to be our basis vector. There's one of them. So we can say here, therefore the rank of our map is also 1. Now the rank nullity theorem, which I'm going to reveal in just a moment, is going to relate the rank of a map, the nullity of a map, and the dimension of our starting space, dim of V. But before we move on to the theorem itself, now is actually the perfect time for you to consolidate what we've learned so far about the kernel, the image, the rank, and the nullity. And the best way to do that is to head over to ProPrep, an online resource which uses video tutorials to help to improve your skills in STEM-based subjects. There's a whole section devoted to the image and kernel, beginning with some short lessons to introduce the concepts before moving on to 17 separate exercises, each with a full video solution. The lesson videos contain several worked examples to help to solidify the definitions of image and kernel, including some questions looking at their dimensions. The exercises range from the familiar in the form of the standard Rn vector spaces to the more exotic with the vector space of polynomials. There are also some more advanced proof-style questions, as well as some involving the matrix representation of a linear transformation. You can access everything by simply clicking on the link in the video description to sign up for a 30-day free trial of ProPrep, courtesy of Tom Rocks Maths. As promised, here is the Rank Nullity Theorem. We start with V and W being finite dimensional vector spaces, and we're going to have a map T, which is linear. Let T mapping from V to W be linear. Then the rank nullity theorem states the following: the dimension of V, which is our starting space, is equal to the rank of the map T, which remember is the dimension of the image of T, plus the nullity of the map T, which again, recall, is the dimension of the kernel. So what this is saying is the dimension of your starting space for any linear map T is equal to the dimension of the image of that map plus the dimension of the kernel of that map. So one way I like to think about it is as follows. The dimension of our starting space, this is representing all of the little pieces, all of the building blocks, the basis vectors, that together make up our starting space. And we're saying if we were to count all of those building blocks, then the number here has to be equal to all of the pieces that are in the image of a map. And remember, these maps are structure preserving, plus all of the pieces that are in the kernel, so all the pieces that are mapped to 0. So you're kind of saying, take any piece in your starting space, and it's kind of got to either go into the image, go into something, or it's got to map to 0. There isn't really anything else that can happen. You can't suddenly lose pieces. Each building block, each piece has to either be mapped to something non-zero, in which case it's in the image, or it can go to 0, in which case it's in the kernel and contributes to the nullity. So every piece has to map somewhere, and so all of the pieces, when we count them at the beginning, pieces at the end have to also be counted, and this kind of hints at this structure-preserving nature of the linear transformations, which we talked about in the last video. So, how do we prove it? Proof. We begin with another topic, which was introduced in an earlier video in the Oxford Linear Algebra series, and that is the idea of a basis. So, we know that the kernel of our map is a subspace of our starting space V. So let's suppose that the kernel has a basis, and that can be V1, V2, up to some number, let's call it Vn. Now, since this is a subspace, this is like part of the larger space V, and we've seen before, again in particular in the video looking at bases, that we can then extend this. So we are going to extend this to a full basis of V, to basis of V, and let's suppose that basis has the same first n vectors. Then we're going to add in v1 prime, v2 prime, up to some number vr prime. So using the definition of dimension and rank and nullity, which of course themselves are dimensions, we can now begin to write some things down. So we can see here that therefore the dimension of the kernel, so the nullity, so therefore null of t is equal to n, because there are n vectors in the basis. Okay, it's arbitrary, but we can still write it down. And then we're saying we're going to extend this to the full thing. So we're saying the dimension of V is equal to R plus n. So we have the n from our kernel, and then we extend it by adding in all these other new bits, the primes, the v primes, and we're going to add r of them. So that's n plus r. So in order for this to be true, we need, so these two things say, therefore we need, or we want, another way to think about it, the rank of t to be equal to r. So we need a basis of the image of t, so let's write this down, i.e. basis of image of t contains r vectors. Now, given that we already have a collection of r vectors over here, we have a very good candidate for what must be in this basis. So we can't just take these things because they're in V, and we want something that's going to be in the image. So the image, of course, is in a potentially different vector space W. But what we can do, since we know that we move from V to W, or we move into the image by applying T, and that's the key here. I'm going to claim, and this is what we're going to prove, I'm going to claim that the collection of T applied to the V primes, so T of V1 prime, T of V2 prime, dot, 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 up to T of VR prime, I'm going to claim that this is a basis for the image of T. Now, we of course need to show this, and that's what the bulk of the proof is going to actually be. But if we can show this, big if, but if we can show this, then this clearly has size R. So if this is true, if we show this to be true, if we show this to be true, then the result will follow. We have rank nullity. Because if this is indeed a basis, which again, recall, means this is a spanning set which is also linearly independent, I'm going to have to show both of those things. But if we can show that, then there are clearly R elements here, and so therefore the dimension of the image is given by R, and therefore we can conclude the dimension of V is indeed equal to the nullity plus the rank. So we need to prove the claim. So as I've mentioned, in order to prove this claim to be true, that T of V1 prime up to T of VR prime is indeed a basis of the image of T, which again will give us the final proof. In order to prove this, we have to show it is both spanning and linearly independent. So, step one, we need to show that it's spanning. For this, we look at the basis that we have over here for our starting space V. Because a property that we have of a linear transformation is as follows. If v1 up to vn, v1 prime up to vr prime spans v, i.e. our starting space, then we can conclude that t applied to all of these individually will actually span the image. T of vn, t of v1 prime, t of vr prime spans the image of t. Now, if you haven't seen this before, or this doesn't feel particularly obvious, we can think about it as follows. Any vector in our space V is a linear combination, and the linear bit here is key. It's a linear combination of all of these vectors. So when we apply t to a sum of all of these bits, because t is linear, it has those structure-preserving properties that we want. Because it's linear, we're going to get a sum with various coefficients of all of these things. So no matter what we start with over here, we are always going to get something that is a combination of those ones. So because this spans our starting space, this will always span the image. Now, our claim of this as our basis doesn't contain all of these vectors. However, the first few in this box, these things are all equal to 0. So all of these are equal to 0 because v1 up to vn belong to the kernel of t. They're actually the basis of the kernel of t. So what does it mean to belong to the kernel? It means when you apply t to those vectors, you get 0. So all of these are actually just the 0 vector. So the actual span is in fact just t applied to v1 prime all the way up to vr prime. So we can conclude step 1, spanning, is true. Now step 2 is to show linear independence. And this one does require a little bit more work. Now when we covered the topic of linear dependence and linear independence in an earlier video in the Oxford Linear Algebra series, I actually said at that time that the easiest way, or the most useful way of showing linear independence, is to consider a linear combination of the vectors and argue that all of your coefficients have to be 0. And that's exactly what we're going to do here. Let's call it alpha 1 times t of v1 prime plus alpha 2 times t of v2 prime plus dot 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 plus alpha r times t of vr prime. Suppose we have a linear combination of our vectors and it's equal to 0. Our aim, which I will write over here, our aim here for linear independence for Li, we need to show alpha I is 0 for all I. So all of the coefficients have to be 0. That's the only way to solve this particular equation. If we can show that, we have linear independence, therefore we have that this is indeed our basis, and therefore we have rank nullity. So we know that t is linear, so let's use that. So we can say, well, t is linear, so therefore, since t linear, we can put everything inside. So alpha 1 v1 prime plus dot 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 plus alpha r vr prime is equal to 0. But now we have t of something equal to 0. So the something is in the kernel. Because what does it mean to be in the kernel? It means when you take t of the thing, you get 0. So therefore, this combination in here belongs to the kernel of t. But we know a lot about the kernel. We know its basis. this up here is the basis of the kernel. So we have something that's in the kernel, and therefore, because we also have the basis, this thing must be able to be expressed as a linear combination of the basis vectors. So that means, because it's in the kernel, that means there exist coefficients, let's call them beta I, such that our thing, alpha 1 v1 prime plus dot 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 plus alpha r vr prime has to be equal to beta 1 times v1 plus dot 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 plus beta n times vn. We have to be able to express the thing that's in the kernel, because we can see here it is, that's the definition of being in the kernel, has to be able to be expressed in terms of our basis vectors. But what have we got here? Well, what I can do is actually just take all of these across to the left-hand side. So I can say, well, that's equivalent to alpha 1 v1 prime plus dot 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 plus alpha r vr prime minus beta 1 v1 minus dot 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 minus beta n vn being equal to 0. So what we've got now is a linear combination of n plus r vectors. Now those n plus r vectors are exactly the basis of V. So this is a linear combination of basis vectors of the basis of V. But those n plus r vectors are a basis. So they are linearly independent because they're a basis, one of the two properties. So we have a linear combination of linearly independent vectors equal to 0. That can only happen if all of our coefficients are 0. Precisely because we know this is a linearly independent set. It's our basis. So that means, therefore, all the alphas are equal to 0 and all the betas are 0. Now we don't really care that the betas are 0. It's something additional that we get, but the important thing for our purpose, the alphas have to be 0. Our secret aim over here was to show the alphas are 0. So we've got it, we've done it. We've been able to show the alphas are 0. That tells us we have linear independence. We put a tick here. We go back to this, put 2 ticks. This is indeed a spanning linearly independent set. Therefore, this is a basis of the image. It has size r, dimension r. We know that the nullity, the size of our kernel over here, there are n vectors there, and V has n plus r. So the rank nullity theorem follows. We have got a proof of one of the most important theorems in all of linear algebra. Now that we have a proof of the theorem, it's time to put it to use by solving some problems. Just click the link in the video description to head over to ProPrep and make the most of your 30-day free trial courtesy of Tom Rocks Maths. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all very soon. Take care.